All right, everybody, I think it's just about that time to get started here. Welcome to a new week, and I hope that you guys are doing well and ready for the rain. We're supposed to get more rain again, I think tomorrow and Thursday. So be careful out there, but in the meantime, just make a few announcements here to get started with. I passed back the exams. I'm not gonna go over the exam in class. I posted solutions. I put a copy in the resources folder, and I also emailed it to you, I think, a few days ago. And keeping in mind, of course, that sometimes there's more than one way to say things. Like the exact write-up that is in my solutions, isn't necessarily exactly what you had to have down. But do take a look over your exams and let me know if you have any questions about it, or if you're still concerned you don't understand how to do something from the exam. Let me know. I would definitely recommend that you should go over it to a point where you feel confident in it. That, oh gosh, okay, if I had to do this again, I could definitely get this stuff all right. And if you don't feel like you're at that point, feel free to stop by my office and we can talk through as much of the materials that you need to kind of see a refresher on as necessary. So this exam doesn't have to be a make and break. Remember that at the end of the semester, I'm going to upweight the best part of your grade to count an extra 5% towards your grade. So whether that's the homework, one of the midterms, or the final, those 5 parts, and I'm going to downweight whatever the sort of weakest of the 5 components was. And I'll do that for each student one by one. It depends on obviously your own individual scores as to which one I'm going to upweight and which one I'm going to downweight. As it says in the syllabus, the midterm was 18% of the grade. But if it's the lowest part of your grade, I'll only make it count 13% of your grade, which isn't that much. If it's the best part of your grade, I'll make it count 23% of your grade. So it can work to your advantage that way. But yeah, if you didn't do as well as you would have liked, there were definitely some people below 50%, even after the adding the take home points and all of that. If you don't feel like this was where you want it to be and you want to talk to me about that, I can be a very good listening ear about stuff like that too. We can try to figure it out. Maybe you just had a bad day, didn't get good sleep the night before the test. Maybe you really didn't study for it the way you wish that you could have, or maybe you want to make some changes for next time. Whatever it is, if I can help with that process and try to get you feeling a little bit more confident and a little better about where we're headed from here, I definitely am open to that. I encourage you to check in with me on it. But yeah, by and large, there was a big span of scores throughout the exam. There were several people in the 80s and 90s, but there was also a number of people kind of down in that danger zone 50 and below, which we don't want to see. I do have a slightly more generous grading scale than a lot of classes. Like usually to get an A, you have to have a 90%. In this class, it's 87.5, and then the B cutoff is at 75. To pass the class, you're going to need about low 60s. I'll say it like that. Low to mid 60s is really what you're going to need to pass. So if you're not quite there yet, it doesn't mean you can't get there. It doesn't mean you can't get there. I'm here to help, and I'll do whatever I can to try to make it happen. But only you sort of know how you're doing as far as did you study enough for the exam? If you studied for 500 hours and still didn't go well, then that's one thing. But if you didn't maybe put in as much effort as you could have, then that's at least encouraging that there's some room for growth there, some room to improve. But again, I'll be happy to talk individually, doors closed, just a private conversation with anybody about kind of where they're at in the class, any questions that you have. Just let me know, and I'll do my best. I promise I will try to make you feel a little bit better about the situation. So anyway, so that's kind of the first section of the class we're done with. Now we have arrived into March, and at the end of this month, we will have another midterm. It's actually on March 27th. So February 27th, now we're gonna have another one on March 27th, which is right before spring break. And so that exam is gonna cover most of the rest of chapter 3, which we're still working through right now, and then we should be getting into chapter 4 this week. And chapter 4 is a pretty heavy chapter about limits of functions, as well as the concepts of continuity and uniform continuity and a number of other things. So it won't be that many sections in this next part of the class, but it'll take some time to kind of go through it. As far as the homework goes, there is an assignment that is due tonight. Oh, I wanted to give you guys a hint on one of them. There's an assignment that's due tonight. It's a short assignment. And I do have office hours later for any longer questions on it, but I wanted to make a quick little hint here about the problem. It's in 3.3, it's number 4. I think it's the last one on the assignment. They give you this sequence Zn, and it is just the sequence x1, comma y1, comma x2, comma y2, and so on. So it just alternates between some x's and some y's, and each of the the x's form a subsequence, the y's form a subsequence, and then the idea is that Zn converges to some number, let's say z, if and only if xn converges to z and yn converges to z. This is the statement of this problem. I can just mention that the forward direction of this is very, very easy if you just look at I think there's only one theorem in this section. So if you look at the theorem, that should pretty much answer it for you. So this is pretty much a one-liner. So I'll leave that for you. If you need help with it, of course you should ask me. But I don't want to steal all of your fun away. To do the backwards direction, you have to be a little careful with this. It looks similar to one that was on the midterm, but it's actually not the same thing. The one on the midterm was, I think I had x1, y2, x3, y4, x5, y6, and so the subscripting was different. And so for this one, I'm going to recommend, first of all, that you sort of try to get a handle on what this sequence actually looks like, depending on whether you're looking at an odd term or an even term of the sequence. You can see that all of the even terms involve the y, right? So the second term, the fourth term, the sixth term. And what would be the subscript on that, by the way? The second term is y1, the fourth term is y2, the sixth term is y3. What subscript do I need here? Say again. I don't think it's n minus 1, because so this is z2 is equal to y1, but z4 is equal to y2, and z6 is equal to y3. And over 2. Yeah, that's going to be the one, right? So it's exactly half of the original subscript. So like the sixth term of this sequence is y sub 3. So you take 6 divided by 2, and that gives you that value. And then, of course, the odd cases are going to be the x's. Anybody have an idea for the x's? Maybe somebody besides Ayushi will tell me what this one's a little trickier because n is odd this time, so I can't just divide by 2. And honestly, I don't have like a great way to figure this out. I just kind of think about it. Okay, the Z1 is X1, Z3 is X2, Z5 is X3. Got it, Brian?
Is it n plus 1 over 2?
That's right, n plus 1 all over 2. That's exactly what it is, okay? And if we're assuming that the xn sequence converges, then this means that there exists an n1, it's a 1, such that blah, 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 right? And then because the yn sequence converges, there exists an n2 such that blah, 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 blah. Now, the one that was on the midterm, because of the way the subscripting was, it was very easy to get the n naught value that you ultimately need to find. Usually when we have an N1 and an N2, what do we take for our final N naught value? The maximum, right? And on the midterm, that worked fine. On this problem, it's actually not going to work. So I'm just going to tell you that N naught is not going to be, it is going to be the max of something, but it's not the max of N1 and N2. We have to, sorry, let me take that back. This is just not correct. You don't just take the max of N1 and N2, you actually have to tweak it a little bit, okay? So if you aren't able to see what it needs to be, you need a little bit of a moment to think about that. So I will let you do that, but if you have a question on it, stop by my office hours later today and I'll be glad to give you a hand. Okay, so anyway, this is one hint here. The hint is don't take this for N naught. Okay, it needs to be fixed just a little bit. So that's the homework that's due tonight. And I have office hours, as I mentioned later on. I already have another assignment posted for you, and that'll be due next Tuesday. So we have a whole week ahead of us to do that. I might be going, it's always so weather dependent with me. I might be flying up to Washington to try to climb Mount St. Helens on Friday, Saturday. So if that's the case, I will be canceling my Friday night office hours and I will email you. I'll probably end up replacing those with a Sunday night hours. But it all depends on the weather, right? When I'm climbing stuff, it looks like right now my friend up in Seattle is saying, yeah, you should come up on Friday and Saturday. So that's my plan. I've got my airline ticket and all that stuff, but I should only be out of the internet access for 2 days. And there should be plenty of time by the time I get back to help you with that next homework if you need it. So anyway, I just wanted to let you know that I'm always running around somewhere. Okay, any questions? Okay, great. So anyway, keep working on the homework. It is a short assignment. If you haven't even started it yet, no problem. You can easily get it done well before it's due tonight. Not a big deal. Okay, anyway, so we had the exam last Thursday. It's been an entire week since we last were looking at this material in chapter 3. So I've reminded you up here of some of the highlights from last Tuesday already. And well, very easy to summarize these 3 theorems, the monotone convergence theorem, the monotone subsequence theorem, and then finally the Bolzano-Weierstrass theorem, which is really just a corollary of the other 2 theorems. It's pretty much got a one-line proof. So again, the monotone convergence theorem, this is just saying that if you have a sequence that's both bounded and monotone, it has to converge. The theorem doesn't tell you what it's going to converge to, but it has to converge to something. And sometimes that's all that you really need to know. Okay, so MCT, monotone convergence theorem. By the way, we proved all of these things last week, right? So I'm just restating the results here themselves. The next one was the monotone subsequence theorem. So if you start with any sequence whatsoever, it will always have a subsequence that is monotone, right? And so if you put that together with the monotone convergence theorem, then if you take any bounded sequence, right, that bounded sequence will contain a monotone subsequence, which will still be bounded also. And if it's both bounded and monotone, then that subsequence converges. I just read out the proof again, right? It's a one-line proof, just putting together the monotone convergence theorem with the monotone subsequence theorem. Yeah, so anyway, so these are 3 really, really big results. This is out of section 3.4 primarily, and definitely worth paying some attention to. Any questions on these 3 results? We did an application of the monotone convergence theorem last week where we had I think it was a recursively defined sequence, which is sometimes well suited to this type of application. So that was a nice one. I'm pretty sure next week's homework has one that's just like that. So you'll want to refer back to what we did last Tuesday to help you with that. The monotone subsequence theorem was a little messier to prove. We had to talk about peaks of a sequence, which is not really a standard thing that we talk too much about, but we muddled through it. We got the proof to work. It wasn't too bad. A couple of cases to go through. And then, yeah, the Bolzano-Weierstrass theorem. This one I have been hinting more at its future applications. We haven't really used it for much so far, but it is going to have some really helpful applications to calculus when we get into the second half of the semester. So it's good that we have that as a tool. Okay, everybody okay? Okay, great. I had mentioned last Tuesday that there's kind of a version of the Bolzano-Weierstrass theorem for sets as well. So a sequence is a set. Let's not kid ourselves. A sequence is a set, x1, x2, x3, x4. That's a set of points, right? But there's actually a way to sort of generalize this Bolzano-Weierstrass theorem to just arbitrary sets, not necessarily a sequence that would be, listed out as a countable enumeration, but it could be any subset of R. And it turns out there is a theorem, a Bolzano-Weierstrass theorem that has a version for arbitrary sets. And it involves this concept of accumulation points. So I've put this on the board. We talked a little bit about this last week and did a couple examples, but it's another one of these definitions that's really, really sensitive to the exact wording. So we have to be kind of careful with it. If we take a subset of R, I'm going to call it A, and we grab any real number X, which on the surface of it doesn't have to have anything to do with A whatsoever. So you take your subset and you take your point. But what would it mean for X to be an accumulation point of A? Well, that's what this definition is. Before I go any further, I'm going to denote this. This is not in the book. I like to use this ACC notation. It's an abbreviation for the set of accumulation points. So X is an accumulation point of A if, and here's one way of stating it, every neighborhood of X, right? So we can be kind of in our minds thinking about it this way. Here's X, and we're going to make some neighborhood, which I'm going to call u sub epsilon of X. And it's just got a radius of epsilon here around X, centered on X, right? Every neighborhood of X contains a point of A other than just X itself. Now, we never said that X had to be an element of A to begin with. So this other than X thing might be kind of unnecessary. If X isn't part of A, then obviously containing a point of A is all you really need to say here. Okay, so every neighborhood, even if it's a very, very small one, right? Even if this epsilon is really small, there still needs to be a point of A in there somewhere. And we can keep changing this epsilon. We can change this neighborhood, make it smaller and smaller, as small as we want, right? Like just as thin as like a penny, right? In a little neighborhood like that, there still has to be a point of A inside of there. Yeah, in that neighborhood, other than X, a point of A other than X. And the opposite of being an accumulation point of A is to be an isolated point of A. But in this case, X should be in A. If you're going to call something an isolated point of A, it should be a point of A that is itself isolated, meaning that you can make a neighborhood. Okay, so not an accumulation point. Well, how would that read out? Something not being an accumulation point would mean that there exists a neighborhood, right? Instead of for every neighborhood, now there exists a neighborhood that fails this condition, namely that it fails to contain any points of A other than X. So you've got an entire neighborhood around X that has no points of A in it. Pardon me? Other than X, yes, exactly. Other than X itself, which is kind of, yeah, trivially part of any neighborhood containing X. Okay, so does that kind of make sense? We wrote down some examples on Tuesday last week. I'm in a little while today, we're going to do a little bit of group work to kind of practice on these examples a little bit more. Just as a quick remark, I think I did write this down last week, but I'm going to go ahead and write it again here, just in case we didn't quite get this down in the notes. And I've got my little recording to do again today here. I forgot my tripod again. If A is a finite set, So if A is finite, then let's just say it this way. Then the accumulation points of A is actually empty. There are no accumulation points of a finite set. It kind of makes sense, doesn't it? So if you take your number line and you have a finite number of points here, if you just have, say, 4 points in your set, I would claim that they are all isolated. There is no accumulation point of A because you can always make neighborhoods that exclude all of the other points. There's some distance between them. So you might have to make it kind of small, but you can always make a neighborhood. And all you need is one. You just need to show that there exists a neighborhood that fails to contain any points of A other than X. So here you go. I've drawn 4 neighborhoods here. For a finite set, you would always be able to do that. Okay, so all of those points are isolated. Okay? But that's for a finite set. I want to talk about infinite sets for the most part. And this is where we can now state our theorem, guys. This is what I was promising you, theorem 3.11. Now, this we did not do last week. And this is going to be the Bolzano-Weierstrass theorem for infinite sets. For infinite sets. So let's see if we can do this for infinite sets. Here's what it says. It's also very easy to state it. Every bounded infinite subset of R. So if you take just every bounded infinite subset of R. So every bounded instead of sequence, now we're saying infinite subset, right? So every bounded infinite subset of R, instead of that it has a convergent subsequence, the equivalent over here is going to be has an accumulation point. Okay, every bounded infinite subset of R has to have an accumulation point. It can't be empty. So if you have a finite set, you won't have any accumulation points, right? Or if you have a set that's not bounded, we won't be able to guarantee this accumulation point either. So, for example, the integers. Maybe I should have put that as another example. Another example here, guys, if I take the accumulation points of Z, so that's infinite, but those are still discrete points, just in the same way that a finite set, you can make neighborhoods. I could make neighborhoods around every integer, just like I did right here on this picture, and have the same exact conclusion, which is that none of them are accumulation points. This is also empty. Okay, so even if you have an infinite set, you're not guaranteed to have a accumulation point. And the problem with the integers is they are not bounded. So, but if you have both, right? This is always what you want to be doing, guys, in Math 350. You have some assumptions here, right? What are the requirements to guarantee an accumulation point? Well, you need a set that's bounded and you need a set that's infinite. You always want to ask yourself, what if I take away those assumptions, right? What if my set is not bounded? Okay, we have a counterexample, right? What if my set is not infinite? We have a remark that explains that isn't true either. So these are always good things to be doing. Does everybody understand the statement here? We do need to prove it. We do need to prove it. So I'm going to try, if you guys don't mind, we'll just start the proof right here. It's not that long. It's a few lines. It'll take us a little bit of time to do this, but we are going to use the Bolzano-Weierstrass theorem for sequences to help us prove this one. Okay, so somehow I'm going to bring sequences into the proof here. That'll be interesting. Okay, so let's get it started. Let's let A be a bounded infinite subset of R. This is what we're going to start with, and we're going to try to find an accumulation point in there. I'm going to start off by just making a sequence. So I said we want to use the Bolzano-Weierstrass theorem for sequences. So guess what? I need to have a sequence in my hands to be able to do that. So I'm just going to let Xn be a sequence of distinct, I'm going to underline that word, distinct points of A. The other thing I like to do with analysis is when I'm reading my proofs, I like to understand, why did I need all of the assumptions? Okay, so if I take the assumptions away, the conclusion is false. So that must mean we're going to use those assumptions in the proof, right? Where are we? Have we used any of our assumptions yet? Let me ask you this. If A was finite, would we be able to make a sequence of distinct points? If these were my only four, remember, a sequence is a function from the natural numbers to the real numbers. So you have an x1, x2, x3, x4, x5, x6, it goes forever, right? If this was my set, could I make a sequence of distinct points? No, because I would be forced to, in my sequence, if I want them to all be distinct, then I can't, that means you can't repeat anything. But if I only have 4 elements in my set, then of course you would have to repeat something eventually. You see what I mean? So the idea here is that this distinct here, this is, I'm just going to add this to the proof just to make sure everybody's got this for their notes. This is possible since the size of A is infinite. So we are using the infinite size of A to make that first statement here. That's right. Okay. Great. Now, so that uses the fact that A is infinite. Okay. It's possible to make a sequence of distinct points. A is also bounded. So guess what? Your sequence of points that's inside of A is also bounded. Okay. So let's add that here. Since A is bounded, then the sequence Xn is also automatically bounded. For sure, because it's inside of A. Okay. We have a bounded sequence. What's your knee-jerk reaction tell you to do with your bounded sequence? Do we have anything about bounded sequences anywhere? Every bounded sequence contains a convergent subsequence. Let's use that. Okay, so there is a convergent subsequence here. All right, so by the Bolzano-Weierstrass theorem for sequences, which is theorem 3.10. So by that theorem, there exists a convergent subsequence. Okay, so we have to have a convergent subsequence, and I'm just gonna maybe write it like this: X and K is the subsequence. Okay, so we were using that notation for it, and it converges to something which I'm going to call X. This is just for some X in the real numbers. And we don't know whether X is part of A or not. Okay, so that part we still need to figure out. We just add that here. Note, X may or may not. We don't know. It may or may not actually belong to A. Even though the subsequence certainly belongs to A. Right? Everything in the subsequence is part of the original Xn, which was a sequence of points in A. But remember, you can, this is also on tonight's homework, right? You can make a sequence of points that's in a set that converges to something that's not part of that set. Real easy to give an example of that. So that's a possibility. But I'm trying to prove what now? That A has an accumulation point. Well, I think I have a candidate now for what that accumulation point is. I would like to show the existence of an accumulation point for A. And does anybody want to help me with that? Do we see one that might be a good candidate? Actually, just X itself, exactly. I'm gonna claim that X is an accumulation point of A. That's exactly right. We're gonna claim that. And just a little bit more room, I guess. Let's try to prove that X is in fact an accumulation point of A. Do that over here. It's the last part. We're almost done. Okay. How do we prove that we have an accumulation point of A? Well, we have to take an arbitrary neighborhood of X and prove that it contains a point of A other than X. Okay, so to do this, to show this, I'm going to consider a neighborhood U of X. Just going to call it U for a moment. Just take any old neighborhood. Now the subsequence X and K converges to X. So since that subsequence converges to X, then what's the definition of convergence? For every neighborhood, including this one, there exists an N naught, right? Such that if N is greater than or equal to N naught, then the terms of the sequence are in that neighborhood, right? In this case, I'm going to call it K naught rather than N naught, because really it's the K that is the driver of the subsequence. So I'm just going to say there exists a K naught in the natural numbers such that if, and then we're going to say if K is greater than or equal to K naught, then X and K is inside of U. Okay. So what do we have to prove now? We have to prove that this neighborhood U contains a point of A other than X. Well, this neighborhood U contains a whole truckload of points of A. All of these guys are in A because they're part of the sequence Xn, which was points of A. And not only that, they are all distinct. Where am I going to use that? Right? Well, what if it was possible that every single one of these values was just X, 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 X forevermore? Well, then we might have trouble finding a point of A other than X. But we know that these points are not just X, 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 X forever, because all of them are distinct. Right. So that means there has to be a point of A other than X that's in U. Okay, so let's wrap that up. So let me just say, since X and K is not equal to X for some K greater than or equal to K naught, right? The terms cannot just become constant equal to X. Then U contains a point of A other than X, namely any one of those X and Ks. Okay, and so that proves the claim, and so thus X is an element of the set of accumulation points of A. So this is what we were hoping to prove here. Does this make a little bit of sense? Yeah. Okay, super. All right. There's actually several ways to sort of explain what an accumulation point is. And I think I'm going to give you one of them right now, and then we're going to do some group work and let you try to prove it. Okay, with your groups. Let me state it here though first, and let's see if you guys think that at least it's reasonable what this is. So this is proposition 3.4. And what it says is, again, let A be a subset of the real numbers and let X be just any real number. So we create our subset, we grab our point X out of the real numbers, And then this proposition, and again, I'm gonna state it in the notation that I'm adopting here. The book will actually write it all out in words, but I'm gonna use my ACC notation. So X is an accumulation point of A if and only if and only if every neighborhood of X so far it's reading just like the definition. X is an accumulation point of A if and only if every neighborhood of X something. Let's just see what this says. This is gonna say contains. No, that says contains too. Over there it says contains a point of A other than X. What this is gonna say is just simply contains infinitely many points of A. It's a little bit more succinct. It's a little bit more succinct. You know, and in some ways, you know, you might, so, you know, you could actually take this as your definition if you wanted to. And using this as your definition, for example, remarks like this just become trivial. What does it say? If you have a finite set, there's no accumulation points. That's pretty clear because there's no neighborhood of anything that could ever have infinitely many points of a finite set, right? So this would never be true, right? If capital A was finite, so you wouldn't have any accumulation points. So it's kind of a nice way to think about it. And you know, sometimes the way things are originally stated, it might make good sense for like writing out proofs of stuff, but sometimes for your intuition, there's an alternative rephrasing that is actually preferable. And this is an example that it may be true for you. Right? It's kind of personal preference, but I like this statement. Right? It's very easy. Every neighborhood of X, I don't have to worry about this other than X thing either. Contains a point of A other than X. That's not even listed here. It just says every neighborhood of X contains infinitely many points of A. So that's pretty nice. It's pretty crisp and succinct. What I'd like to do is let you guys try to prove it. It's actually not that bad. The backwards direction is pretty much you just go straight off the definition. Okay, I mean, if you assume that every neighborhood of X contains infinitely many points of A, then wouldn't you agree that every neighborhood of X would have to contain a point of A other than X? Oops, I just did half the proof for you.
Okay, so the other half?
I gotta stop. I'm gonna let you do the other half. For the other half, you're actually gonna wanna do it actually by way of contradiction. The forward direction is the harder part, right? So suppose there is a neighborhood that only has finitely many points of A, and see if you can contradict the definition of accumulation point. So let me pass this out and give you guys a few minutes. There's also a second problem here too about accumulation points that might be good to talk through with your group. And I will let you guys come up to the boards if you want to. Is everybody following this okay? So far? Is that making sense? It's a lot of just wading through definitions, to be honest with you. 2, 3, 4. 2, 3. Okay, guys, you can come on up. Use as much board space as you would like. And I will get some of this other stuff out of your way for you. Keep this definition with you when you're working on it. Okay, I'm gonna erase it right now, but you're gonna need that definition to do this problem. Grab 2 or 3 people and come find some board space, guys. Main thing is I want everybody kind of up and out of their chairs. It feels like a Monday to me, even though it's Tuesday. Come on down, guys.
Says something about.
You guys are gonna have no mistakes, right? I'm just teasing.
On the other side.
On down. You guys wanna speak over there? Maybe you guys can
Yes.
buddy up with these guys here.
I don't wanna show my work on the camera.
That's okay. Oh, you don't want that? Well, here, I'll go like this. Feel better? Okay. So go by contradiction, guys, on the forward direction. Prove it by way of contradiction. I'm sorry. I'm not actually saying that the A is that result. I'm just saying, suppose that there are, these points, that are in this neighborhood. It's not actually a capital A, it's equal to as a set. Correct the word in a little bit. Assume there is a neighborhood of X that only has finitely many points of A in it. Does that help now? Still won't help. So by way of contradiction. This is.
I was like, I can't remember, no, I saw this, but I can't remember.
That's what you're contradicting, so we need to say, assume that there exists a neighborhood of X containing finite many points of A.
No, you don't need to write that, just wait, like. Where's the bottom part? I wouldn't do this, so just write the if and only if statement.
Say. Oh. That's right, that's exactly right. This helps to have pictures. Say A1 is there.
Did you make them say?
Say there's three of them.
Infinitely.
No, there is no.
And your job is now going to be, actually, let's make a fourth one.
Yeah.
Like a fourth one.
Uh-huh.
Your job now
Points
is
of
to
it.
contradict the definition of accumulation point. So if you need to, take a look at that definition. That'll help you.
But I remember what I mean.
Every neighborhood of X.
So we're
going this way, so you're assuming that I. Oh, I don't know if that's really like concrete enough. It's just probably not. I like that. These are saying.
So let's finite.
Every neighborhood of X contains a point of A other than
the A is R and X is R, then X is.
Your job now is to contradict the definition of.
Chief.
Try to show that actually and maybe. Okay, so look back at the definition.
Okay.
Just picture mine. Start your intuition a little bit about how to do it.
Means a point of A.
So like other than that, so every neighborhood of X contains a neighborhood of A other than.
We'll think it, let's say.
Help you with the intuition here.
So then, I mean, you know, by way of like. Not.
Then that's make it smaller.
That has only finitely many points.
So-
Just for the picture, I'm just.
X is not an accumulation point.
Like,
X is a add-on, let's say,
Suppose you
power
have
up.
this neighborhood and it's only-
So then X is an isolated point of A.
Now what you wanna do.
That way it's for every neighborhood, so then if we keep making our neighborhood smaller, eventually it'll
What
run
you're
out.
trying to show is that
Because it's finite.
X is not an accumulation.
So then there's no.
Then there's not a point, then it can't be.
Accumulation point of A, so that was every neighborhood, including this one.
Contains that, but it-
A other than X.
Is that what you were saying?
Every neighborhood. You've got one neighborhood. I bet you could draw.
So you have to take 8 patterns.
What needs to be a neighborhood of X? Yeah, so it has to be centered on X.
But it's not.
Draw a neighborhood of X. There we go. We can draw.
Wait,
a
how
neighborhood
better-
of X that does not contain any points of A. Other.
No, you don't.
Proof by picture.
No.
That's definitely the intuition. So what they have to do for this, guys, is figure out what's.
I know.
What is the epsilon radius?
Sorry.
of X that we need?
Yeah.
That's the trick.
There's a.
Like how small does that neighborhood have to be?
Then yeah, A1, and one of those is close to zero.
So how?
Then just half
Well, I always get this confused by
Oh, wait a second. If we're doing it by way of contradiction, then we're negating this part. And then we're, yeah, so we're keeping that positive and, sorry. So assume X is an accumulation point and that there exists a neighborhood.
So like, so.
Yeah, call it U of X with only finitely many points. And then the hint here, I said you could call them A1 or A2 up to A. Okay?
That's where I always get mixed up with the way.
Yeah, it's setting it up is super crucial. So let's just draw the X here. I just want you to have a little intuition on it. Here's my neighborhood U, and it only contains, let's just say it contains 3 points of A. It says here with only finitely many points of A, sorry. So there they are. There are the 3 points. And now what you need to do is contradict the definition of accumulation.
Yeah, that's about it.
That's gonna be the main thing. All right? I will come back and check on you. Does anybody need a hand?
I was thinking. Um,
Right, like something like that, like, whatever one's the minimum distance from X. Whichever one exists in this like
Translation
original
point.
form,
no.
original, like this is the.
Or
those
then
G
you're gonna have
Everyone
A
thinks
being
not for
finite.
You take the minimum of whatever
it's finite,
this
then
distance is, and you divide by half and make a new one, then they're just not exist a point.
That's true.
So then, but I'm pretty sure we have to take
That epsilon.
the definition of
Right,
the
ID.
accumulation.
But
Right?
Yeah. I support you.
So then there's this new-
I don't know if it's like as formal as it should be.
finitely many points of A.
And we're saying that there exists.
Then we're actually.
I would rather do that. Body like it makes sense to me. Like, I don't think it's gonna.
Now, your job is to contradict the definition of accumulation.
So let's see.
So you need to find that. How do you find it? That's the crucial thing. How do you find the radius? What radius of X would work right here? So we have no other elements of A. In the neighborhood.
Oh, I could do this, I could do this.
Picture will help you.
So then,
Good, I'm just gonna rewrite it. You really want to have anything on the outside.
Well, but that basically is the definition. But we need to come up with
You have the right-
that definition. Just basically what he is telling us to do. So then, because then, can you say then since A is,
Since A is fine.
then there's no accumulation going A? Couldn't we say that?
I think that's a remark.
I mean, but
Then.
Mark is kind of just a tree.
Whereas.
He was saying, but then we were asking schools.
Say, I mean, these are all positive, but this minimum could be actually.
Why?
Anyway, you guys are doing great. Concentration is stepping less than. Try to show that that's not an accumulation point. How is that?
Wait, backwards.
So the bar was hard, right?
Oh, that was.
I actually think this isn't quite gonna work, so first of all, that's negative. And I don't want my epsilon.
It's just a definition.
So the epsilon neighborhood that you're making has to be positive. Like what if X is, I don't know, X. could be negative, these could be negative numbers. What you really need to do is make this neighborhood small enough radius that it doesn't trip over A2.
Wait, well, why is that negative though?
Well, for your, if epsilon was negative, this would mean.
Oh,
negative sign, right, to make this neighborhood would make sense. So the epsilon should be greater than
No, we
zero,
could do that.
for sure.
Right.
Something like that. Like, so taking a minimum, I'm gonna quibble with this subscript in a second, but you're on the right track here, right? Yeah, and the actual radius is being dictated not by the A values, but by their distances from X. Like how
Oh,
big
yeah.
of a distance is this?
Yeah.
So what you really wanna do, yeah, and we actually need to take the minimum of all of them, because we don't know which
Right.
one.
Well, here it says, they're listed.
Oh, you did? Oh, I didn't
So
see
yeah,
that.
then I was probably like, you say absolute value.
I think it would be clear to. This is your. Okay. That was what I was gonna quibble with, yeah. Now, it's very important that this is finitely many points, and that was part of your assumption, finitely many. Because if you take the minimum of an infinite list of numbers, right? If you take an infinite list of positive numbers, let's say 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, forever, right? The minimum of that infinite list doesn't really exist, or if it did, you'd call it the infimum, which would be 0. And you're not allowed to have a neighborhood of a radius of 0.
That would be good.
So that's actually a subtle
Wouldn't
issue
you,
about
since
where
they're
the
finite and many,
finite.
to be able to get a neighborhood A1?
Because this is
X
only
not in-
finitely many high
That's
values.
not an accumulation.
Right, A1, A2,
Make a
A3.
neighborhood
So you can
around
take a
A1,
finite
make a
list of
neighborhood around
positive numbers, these are all positive.
You can make a neighborhood
And
around
the
X3
minimum
that
of
doesn't
will
include
always
X.
be positive.
So then they wouldn't, X
Not
wouldn't
0,
be
right?
an
No,
accumulation.
so
point.
just to really emphasize that point, I
I
would
think that's what
probably
he's
just
saying, is like,
tack
you need to
that
make a
on
minimum
there, that it's strictly
of
positive.
those.
Now you've created a neighborhood
Since you can make those.
that does
neighborhoods.
not have an element of,
I just don't know how to
A.
state that.
other than X. Because you've made this very small neighborhood that's excluded all of these other points.
So it's like, you could,
Make a little bit of sense? Okay, that's how it works. That's how it works. Good job, good job. All right, maybe we can, get you a better marker for one thing. You wanna take over for the next one? All right, go for it.
I don't
See what you can do.
know how to state it.
Let's see.
I don't know how to state this. Like, I
Okay.
understand the reasoning.
You understand the
but I
idea?
don't understand, I don't know how to
Guys,
state it.
these neighborhoods are not being centered on the A. They have to be centered on the X's, on the X, sorry. So the neighborhood has to be centered on the X. Based on this picture, Could you make a neighborhood of X that does not have any of these points of
Yeah.
A in it?
Yeah.
Make it really small.
Really small, right around X, yeah.
Right? And now, what was sort of the guiding principle about how big of a neighborhood it could be? Right? It was X, I didn't compare X with A1, I compared it with A2. Well, why did I do A2 instead of A1?
Because if you did A1, then A2 would be in part of the neighborhood.
Right, so what you're really looking for is the point that which of these A's is closest to X.
Okay.
The minimum of all of those distances. So this is actually the key idea. I is 1, 2, up to n, right? So you take the minimum of all those. So you see, how far is X from A1? How far is X from A2? How far is X from A3? Take those three numbers, whichever one is smaller, that's the neighborhood, that's the radius of the neighborhood I'm gonna use. And this will be greater than 0.
Okay.
Because you're taking a
Yes,
big value of a bunch of positive,
Yeah.
these are a bunch of positive numbers. Taking the minimum of it. And now that contradicts
The other direction.
That's
ACC. Because the definition of ACC is that every neighborhood
So you
of
basically.
X contains a point of A other than X. Not this one, not this one. So if you make your neighborhood with this radius, technically now what we need to do is we need to make this neighborhood. Right, that does not have any points of A other than X in it. So in other words, this is now empty. If I forget about X itself and I look, well, what points of A are inside of that neighborhood? The answer is none. You can see that there's no points of A inside of that neighborhood except maybe one. So that's the negation of the definition of ACC.
Okay.
And so you're. Well, the accumulation point definition is a little bit.
Yeah. It's kind of funky to work with.
Yeah, definitely, definitely.
Where's the definition?
You guys can help this guy out. Don't let him stand up there and stage fright.
Do it all by yourself, Alex, go.
Okay,
What is the definition of that?
then there are X and Y in all are correct.
Yeah.
X less than Y, there exists an element of A.
Okay, sounds good. And.
I mean, it makes sense, it's just like, how do you think about it? Yeah.
And it should work great.
I agree.
Backward track is sort of a.
Or X
It's a
less
free.
than Y,
More or less.
Oh, backward structure. Definitions.
and then small a and A.
Then of course, small a.
They're in, like, exist in large A, like the exist sign, whichever, if that works too.
Pretty much. By
Yeah.
definition.
Like there's a small a in A such that
Very nice.
X is less than A is less than Y for all X and Y in R.
So actually, I would say we're not ready to slow down.
That didn't go well.
Actually, we're actually, no, I thought this was draw this picture here. We're in fact, and there's this neighborhood of X that has only finite points of A.
There was a thing.
It's just about these.
Oh, so like we had to use it, and so, yeah.
We're not gonna just.
No, I think you're right. I think
When
we
you
did
set
that.
that up for variables are we given, that's
Why?
I think I got wrong.
we don't have any idea.
Bad Alex.
Actually, what you want to do, you actually wanna make an epsilon. You wanna make the.
Between any two distinct real numbers, there exists an element of A,
Predict the ACC.
as long as A is a subsequence.
You can say for all X
Let
and Y in R.
epsilon, I would just say equal the min of all of these guys, right?
Okay, so that's my definition.
Like so.
Since
And that's
the neighborhood
greater than zero.
contains infinitely many points, by definition, X is an accumulation of
This neighborhood.
I mean, you could say, right, smaller X's, Y's. And there would still be.
Yeah, I know, it's a lot of writing.
Yeah, so we know that.
I don't think we need to write it in again.
Points of A.
By def, X is an accumulation point of X.
Doesn't contain.
That every neighborhood of X
Of
contains
A.
A other than X.
Other than that.
That's why I needed my phone.
These are a subset of.
And that was more.
Other than
X
Also.
also.
Yeah, and then maybe just like you see points that. Take another way,
But what if he is?
That's probably what you.
So.
We're on the right track.
So the.
That's how you have to make your raises.
Mark.
It's not so much.
You're literally.
Yeah, I'm saying no matter where we, like, if we pick 4.1 and 4.2 and A is then that means there's some form of
That's also.
Yeah. just, well, it's in A, yeah. So
Forward
we're
direction.
just trying to say the accumulation.
Oh, the one.
Yeah. That there's any accumulation of A is that every neighborhood X.
It's
Yeah,
probably.
we know.
A is
Well,
dense
that's
subset of R.
It just makes sense.
That's the biggest problem.
You take-
Understand the logic. How do I write this?
That would be true. That would be true.
Like that's a good first step, at least I believe it. I don't.
Yeah, I buy it.
Trying to like prove something you don't believe, that's.
We'll have the results on Monday. More or less like prove it to ourselves. Perhaps if you should be, more or less. Okay.
So that,
So.
I
I think the same line.
then subset of R, then.
X is an element.
R.
It's like with A, it should exist in R, and then it wants to that.
Should have brought it.
Then this is-
That's what's already too.
Like to prove equality of, like, cause these are.
As I look
like,
at my
two
picture
sets,
from Knott's Berry Farm.
Like, if, huh?
As I look at my picture from Knott's Berry Farm.
Here, and what is
That
that?
been there.
Well, I'm making that.
That is true.
Prove that the
Prove that if A is dense.
So I, how far is X from A one? How far is X? from
Yeah.
A2? How far is
I
X?
think
from
that
A2?
would be better.
Whichever one is the.
Is a dense subset, is a dense subset of R, then that.
Like, we could call this like A, that was probably better for A.
This neighborhood. So then this neighborhood doesn't have any points of A.
Right. Like, you think that was,
Other than possibly X. I'm sorry?
and then
Oh,
we can
absolutely.
use the fact that
It
it
is
is
important.
to help show that it
This
does
is
that.
exactly the.
Is that like your, you know,
What accumulation points.
accumulation, but this is.
For every neighborhood. There always exists.
It could be.
Here's a neighborhood. And it doesn't have any points in the other.
Because sometimes like, equality, we can just like. Like,
It's
I'm
the
not really seeing that.
Maybe it's.
Which is why I wanted
Yeah, it's.
That's it.
Maybe this is basically. X
Uh,
equals minus A, then you need-
Yeah, like, fine, start writing.
So, yeah.
No.
Probably.
Or does it need to be dense?
And then that's the point.
So.
Even though it's not stated that it's.
Distinct integers, which is something I forgot to put on my test. You can find other.
So A.
Not integers, real numbers.
Oh, that's it.
Whatever you said.
Yeah, he could make that work. He could make that work. So it would more or less come down to the same.
Great.
Great.
Or in this case.
Let's take the point today.
Right? I have.
Maybe not A.
Oh, we come out of that.
Other than X, why?
Exists
Other than.
limits of.
Can I jump in for a second here? So you're proving this, right? Okay. Everything is a subset of R. So we don't have to do anything for going back. R is the big, huge, real. It's really this direction. That's where we have to do it. And so we're gonna grab it as R. And we need to show that, that X is an accumulation point of X. Here's X. To show that it's an accumulation point of A, you have to show that for every neighborhood of X, there exists a point of A inside of it.
And then we know that.
Yeah.
So that's why-
Just double check that for yourself, but that's, it's really short. How we doing? So between any two, so this is what you're proving. Now, this is already clear, because everything is a subset of R. R is the big whole entire real number. It's really this that's more interesting. So how do I go there? I pick an element of R. And my goal is to show that it's an accumulation point of A. There's my X, it's on the real number line. I've got to show that it's an accumulation point of A. What's the definition again? Every neighborhood of X contains a point of A.
Contains the point of A that is not X.
Well,
Yeah, you got
A
it.
is
Just start
dense.
Then there's another point somewhere.
There's another point in here somewhere, right? So there's inside this, remember the definition of dense is something like,
Between any.
between any two, in this case, I'm thinking of X minus epsilon and X plus epsilon. So you make this arbitrary neighborhood of X, and you gotta find a point at A inside of there. Well, you can just say that since A is dense, there does already exist a point.
We can just make this covering and minus some in size.
And we don't even have to show what point, huh?
You don't have to show one point.
Doesn't even give us what
Just have to-
point, just says
So I'm
there's
gonna
one.
say, I'm just gonna say, for every, X minus epsilon to X plus epsilon, pick any neighborhood whatsoever, since A is dense,
But at least we're all on the same page.
since A is dense, there exists an element of A in that set, in that neighborhood.
Yeah.
Right?
Yeah, basically.
That's basically, it's like 1 second. You guys feeling okay about it?
I need to start looking at these.
Yeah.
An equal sign, I don't think so.
In that neighborhood, is gonna find an element.
Usually do something.
I like it, so you like it. It's a great picture. Love it. So you start with X, you make your neighborhood around X, right, goes from A to B, and in that neighborhood. Since A is dense, you'll be an element of A, and I guess you're picking this half of it, so that would mean somewhere in here is your winning point. That does it. I'm sure your partner is good, so.
I'm gonna write it down.
I feel like it's it's more defining a single point rather than the whole set of real numbers, so how would that distinction be more clear? Cause like.
I feel like we want to say
Like,
the
in
need
terms
there
of,
existed
like, adding
A.
and, cause I feel like
It,
if we don't have
right?
a subscript, it's just like,
A is
okay, I'm
dense
done it
in
for a
R.
single point.
This A
And I gotta
is
do a million times for a million other.
You
Yes,
do,
exists
but
in
see,
there.
when you're, just think of this as you're proving
yeah.
that these two sets are equal. So I have to
We
prove
just
that
wanna
this one
define
is a
for
subset of this
every
one, and this one is a
X
subset of
minus
this
epsilon.
one. This one being a subset of this
Or
one is
X.
clear, because everything is a subset of R.
X.
But then I gotta go the other way. I pick an element of R and show that it's.
Yeah.
So I do get to pick one single point, if that's what you're asking. So I do get to say, let X be a
Maybe, or is that- that's
specific
implied.
point of R, and I don't have to over and over and over again, imagine that the X, X, that this argument. Or write down.
Out here.
So where.
I just trying to understand. Yeah, let me see.
The same, so I make a neighborhood out of X, I don't care whether X is
So there's a neighbor.
positive, negative, zero, whatever, or just whatever it is, it was given to us. You just make any neighborhood of X, which is this interval from A to B. And say, well, inside of that interval, I would like to find a point at A. So that's kind of the definition of the accumulation point, right? To be an accumulation point of A, we need to show that every neighborhood of X. And so that's exactly what this is all about. So here's a neighborhood, A is dense, so there's an element of A within every neighborhood that you can ever draw. And that's how it works.
Is this restricted to only a portion?
Yeah, I think the reason for that is just so you don't get X inside of your. Just because it needs to be a point of A other than X. So, but yeah, it's just that short.
Yeah. For any.
Oh, here's my solution. Let X be arbitrary. Consider any neighborhood, X minus epsilon to X plus epsilon. Since A is dense,
then that neighborhood has to go in point of A.
Of course. Okay, that's like that simple.
Instead of
Any
A and B,
neighborhood.
any neighborhood.
Any neighborhood.
Okay.
I felt like it was growing like one case and that's not satisfied.
No, it's an arbitrary neighborhood. Definitely an arbitrary. neighborhood.
Maybe we can always-
I always do it on this side, even if.
I'm gonna jump in because I wanna wrap this up. What we do here, guys, we take any real number X.
That's between.
And I wanna show that this is an accumulation point of A. How do we do that? We take any neighborhood X, and we have to show that there's a point of A in there other than X. And A is dense. To the real numbers, which means if you take any, remember what
Yeah, I
that
heard
means? If I take any two numbers, one less than the other, there's a point of A inside of there. All right, well, then you're done.
So. The next one over here, we got
It's
inexistent
literally,
numbers.
that's literally the whole.
Smaller than
Since
this one.
A is dense, if I make any neighborhood around X, there'll be a point of A inside. Yeah, we just learned that there'll be.
Yeah.
There
is dense, but the movement
not just one. So there'll be lots of points of A inside.
30, 20 something, so it's better than last time.
That's our last one.
You do, but guys, let's not make this too crazy. This is,
Just greater than it is.
this is completely true. Everything is a
It's
subset.
actually fine in there.
R is like the big entire real number. So it's really not part of it. And to do that,
This is greater
we
than
start with X,
Finally,
prove,
in Y.
prove that X.
She's the one who got the 89 and 90.
Also, I was gonna be.
Yeah, I knew that, cause once I saw the, must be a line.
Hey, guys, why don't we take a break until about 3:20 or so, take a short sick leave? Is that okay? Oh, 4:20. 2:20. Oh, I am so messed up by that clock. You know what? Next week it will be right. So there's no point in changing it back because this weekend our clocks are going forward. Anyway, so I was mixed up about the time. We'll start up again at 2:20. You guys, we're springing forward this weekend.
No.
You don't want to spring forward?
It's too-
I love springing forward because then it's light at night.
I
We'll get out of
can't.
class and you'll have so much daylight.
That's one thing I'm happy about because walking out of here late, yeah, like around five-ish.
I know, I can't stand it, it's dark so
Yeah,
early.
it's Sunday, 4 hours Sunday.
Exactly.
So we can, so you did your X is less than Y. Basically, that's the conclusion of it.
This is totally clear, right? ACC is a subset of R, that's good, everything is a subset of R, and it's really the reverse conversion that's the way the real world is. You take, actually, you just need to take one real number here. Just take one X, and you're gonna try to show that X is
I'll
an
start.
accumulation point of A.
A week or older than that.
To do that, you need a neighborhood. Okay. You're telling me, this is for the, this is way more technical than
Way more.
But just take your neighborhood, okay? Okay, what have we just proven the proposition? If every neighborhood of X contains infinitely many points of A, then we're done. Well, the thing is, A is dense. So if you take any neighborhood, there exists a point of A inside of it. And so that's it. That's the whole
So we don't
proof.
have to do the definition.
No, no, that's.
That was fun
way-
figuring out though.
Yeah, it's a reminder how that proof works, but yeah, you do not need to work with that part. Yes.
Oh, whatever.
All right.
It was fun to see it again.
Well, you know,
I think I was more than this one again.
go. Oops, sorry, there you go. Are you sheet? Let's see. Sorry, I ended up grading the original. I didn't let you change your problems. All right, so that was. Sorry, no, you're good. It's right on your desk.
Oh.
I just thought that.
Me? I once, this is my family, my feeling.
That's not too bad. Okay. It's not too bad. An hour for here.
It's very boring. Sometimes.
To drive to
Yeah.
Mexico?
The first one.
Yeah,
is like-
like the-
Oh,
But, yeah,
Not
when
too
I
much.
show it's kind of boring.
Oh, really?
Everybody's there, like.
Oh, okay. Oh, didn't realize that. There are a couple of things. That's not all I can say. Wineries. Yeah, I don't like wine, so. That's it. Oh, okay. All right, guys, I think I'm gonna go ahead and get started here again. This group work that we just did is actually a new one that I hadn't ever used before, so I inserted it into the group works. If you've been following on the Canvas page, I've got the entire semester's worth of group works there, but I decided to insert this one as a new one. So I had to do a renumbering thing so that this would be group work 4. So just if you are wondering why things are a little shuffled around in Canvas, that's the reason. But I do have these solutions in there. You can see it's not very long. It's just all about having the right thing written down. And the definition of accumulation points being a little bit sensitive to the actual wording and everything. So anyway, that'll be there for you if you need to review it at all. I'm gonna spend the last half hour today, guys, talking about a different topic. You might recognize this problem here from our midterm that we just had last Thursday. I gave you this sequence and I asked you to show that it converges using the definition. Okay, now one of the problems with that is that in order to prove that xn converges to x using the definition, you have to know what x is.
you have to know what X is. Now, because the definition, you have this thing about xn minus X being less than epsilon. So you have to figure out what X is, right? Now, in this case, nobody had any trouble with that. I think everybody pretty much 100% figured out that it was 3/2. You can figure that out, and then you know what your X is that you're working with, right? But it's not always that easy to know what the X is. I'd like to write down another sequence for you. So basically, showing this requires us to know that X is equal to 3/2 for the definition. If we're gonna prove it from the definition, I know we have limit theorems that we can use instead, right? But if you wanna use the definition, you actually have to know that that's what the X is. But let me give you another example of a sequence, okay? Here's my sequence. Xn is equal to 1 plus 1/4 plus 1/9 plus ... plus 1/n squared. So x1 would just be 1, x2 would be 5/4, and so on. And, I might be asking you, does this converge or not? And if it does, prove it. And the trouble here is that we may not know what this converges to. If we want to use the epsilon and naught definition of convergence, we have to know what it converges to in advance. Does anybody happen to know? Have you ever seen this one before? This is actually a famous one. It's very famous, almost, you're on the right way of thinking about it. This is a bunch of rational numbers being added together, and it converges to pi²/6, believe it or not. Now, you probably wouldn't necessarily have known that, but you'd like to prove that this sequence converges, and yet you don't know what it converges to. That can be problematic, right? By the way, this is usually proven. This is just a side comment. We're not going to do it in this class, but this is usually proven using the theory of Fourier series. So this would be maybe something for Math 406 for the applied math students. It's more on the sort of pure side of applied. It's kind of on the interface between pure and applied math. But you can use Fourier series, which is basically representing functions using sines and cosines. And as soon as you got some trig functions in there, you start to feel a little more comfortable about having pi in your answer. But yeah, that is not clear at all. That is not clear at all. And so I'm starting to wonder whether we should try to develop some tools for convergence that don't require us to know what the sequence converges to before we can go anywhere, right? So there is a tool that we have for that, and it is what we're going to talk about for the rest of today, and probably a little bit spilling over into Thursday, which is the topic of Cauchy sequences. So I'm going to talk for a minute about Cauchy sequences. When I first write down the definition, it's going to look like it's a weaker concept than convergence, but then in a few minutes, I'm going to prove that actually it's not weaker at all. And in fact, it's equivalent to it. So let's put a definition down here. Definition here, okay? So a sequence Xn is a Cauchy sequence. It is a Cauchy sequence, and these are going to be important later in the semester as well. If for every epsilon greater than 0, there exists an n naught in the natural numbers such that if I stop right there, so far it looks just like the regular definition of convergence, right? Xn converges if for every epsilon greater than 0, there exists an n naught in the natural numbers such that, and then we have the blah, blah, blah part. Well, that's what's gonna change here. Namely, it is going to be if n and m are both greater than or equal to n naught. So I have two subscripts now, n and m. Then the absolute value of xn minus xm is less than epsilon. So this is sort of a weaker definition. It's not telling us what the sequence converges to. In fact, it's not even telling us that the sequence converges at all. It's just telling us that if you give me an epsilon, I can go far enough down in my sequence so that any two terms are within epsilon of each other. This is the definition of a Cauchy sequence. And it turns out that in the case of R, so in the case of the real numbers, right? This is equivalent to convergence. This is going to be equivalent to convergence. In other words, if a sequence is a Cauchy sequence, then it's going to converge. And if it converges, then it's going to be Cauchy. So it's literally the same concept if you're working in the real numbers. Now, so let's actually state that. This is a theorem, 3.12. Theorem 3.12 just says that a sequence xn in R is Cauchy if and only if xn converges in R. Converges to some real number. Okay. So that's the idea. Now, I should make a remark here. We're going to prove this in a minute, but before I prove it, I want to make a couple of remarks here to try to help us think about this a little bit. Theorem 3.12 fails over other domains. So it works great for the real numbers, for R, the entire real number line. But if I go to other domains, it may not work. For example, let's give an example of this. Let's take the sequence xn equals 1 over n. We've looked at this many times. So 1, 1/2, 1/3, 1/4, and so on. This is a Cauchy sequence. Now, that may not be 100% obvious. I would have to prove that. So just take my word for it that it meets this definition. We just wrote down this definition, so I know we haven't had a lot of time yet to get comfortable with it. But we could prove from the definition of a Cauchy sequence that this is a Cauchy sequence. And by the way, it's a Cauchy sequence of values that are all, obviously, I'm going to make this new domain now of the interval 0 to 2. So all of those numbers are between 0 and 2. 1, 1/2, 1/3, 1/4, right? It is a Cauchy sequence, but it fails to converge in that same domain. In that open interval 0 to 2. So here we have, guys, we have a Cauchy sequence that doesn't converge. Now, it does converge in R. It just doesn't converge in that domain, in that interval from 0 to 2. So I've tried to emphasize the domain here, right? Where are we viewing this sequence as belonging to? So I think that's really the main point I'm trying to make here. Okay, everybody with me? I'm going to try to prove this theorem, and this theorem takes a little bit of work. Okay, so I'm going to need probably the longest proof we have to do today. Okay, it's a little bit longer even than the accumulation points thing. So I'm gonna try and do this proof of this theorem here. And then we'll look at some examples again, okay? So we have to prove this in both directions, because this is if and only if. I'm going to prove the backwards direction first, the arrow going in reverse. Somehow this should be the easier direction. Because we're assuming that the xn does converge already. And now we're gonna prove that it's Cauchy. Cauchy seems weaker, right? The definition of Cauchy, we don't even know what the limit of the sequence is, right? There's no mention of what this thing is converging to. It looks like a weaker notion. Okay. According to this theorem, let me just, before I do any more on the proof, I just make sure everybody understands this. According to this theorem, Cauchy and converges are the same thing in the real numbers. But they're not the same thing in some other domain. If the only domain we ever cared about was the real numbers, we would not make we would not make this definition. Because if it's the same thing, why would we have two words that both mean the same thing? That would just be confusing. It reminds me of I was so confused as a student. Some concept of linear algebra, it'll come to me. In some concept, I think there's two words for it. And I kept thinking, oh, this must be two different things. So you wouldn't make this two words that mean the same exact thing. And that's what you might be thinking here. Why do we have this word Cauchy when it just means the same thing as convergent? Let's just call the sequence convergent, right? But it's because in other domains, the two concepts can be different. Okay, but at least over the real numbers, this definition, which looks weaker than convergence, actually is just as strong as convergent. So anyway, but we're going to prove the easier direction here first. I'm going to assume that my sequence converges. Let's give it a limit here. So let's suppose that xn converges to x for some x in the real numbers. Converges in R, so it's going to converge to a real number somewhere. I want to prove that that sequence is Cauchy. How do I prove that something is Cauchy? Let's read the definition. For every epsilon greater than 0. Stop right there. That means that the first thing I'm going to do is get my rubber stamp out, and I'm going to say let epsilon greater than 0 be given. Okay. And my job is to come up with an n naught for this definition. But since xn converges, I already have an n naught coming from that definition, right? So the definition of convergence is, I'll just say, since xn converges to x, there exists an n naught in the natural numbers such that if n is greater than or equal to n naught, then the absolute value of xn minus x is less than, what do you want me to put there? Let's put epsilon there. We're going to find out in a minute that that's actually not going to be the right thing. But let's just put it there because I like to play like a mathematician would play, which is, that's probably what you would think to do. So get your eraser close by. I'm going to be editing this in just a minute. Okay, but it's close. It's not, it doesn't need a big edit. Okay, but anyway, I do have an n naught now. And so I'm just wondering, will that be the n naught that I can satisfy the definition of Cauchy with to finish this proof of the backwards direction? Let's try it. So we found our n naught. Now what do we have to check? We have to check that if we take two numbers that are both greater than or equal to n naught, that we can make that inequality work. So then let's let n and m be greater than or equal to n naught. And then let's take a look at the distance between xn and xm. wondering, does anybody have any idea how I can possibly say anything about this? It's just so weird. Xn minus xm, obviously I don't see it anywhere in the proof, but I don't have very much to work with here, since the whole proof is right here so far. It's like, where do we go from here? Have to do a little trick here. Yeah, you know, I know something about xn minus x. I don't know anything about xn minus xm, but I do know something about xn minus x. So you know what I'm gonna do? I'm gonna feed that in. This is this trick, and we have seen this a few times. I'm going to just subtract x and add x right there inside those absolute value bars. And I'm gonna just treat this as, you know, sort of this quantity plus this quantity, right? And now what do you suppose I'm going to use?
Triangle.
Triangle inequality. This is less than or equal to absolute xn minus x plus absolute x minus xm. Now, in order to finish our proof, we need this thing to be less than epsilon. But if we look at what we're going to get here, I know that xn minus xm will be less than epsilon. And same thing here, because the m is also bigger than n naught. So this is also an epsilon. So now you see why we need to fix things a little bit.
Yeah.
I need to go back. Okay, this is where I said this epsilon isn't quite right. We're going to divide it by 2 here. So that means I have to fix it here too, and I have to fix it here too. Epsilon over 2, epsilon over 2. Okay, you add that up, you get your epsilon, and we are good to go. We are good to go for the backwards part of the proof. That is the backwards part of the proof. Lizzie.
Why did we get rid of the equal sign under the inequality?
Oh, because this is strictly less than epsilon over 2. You talking about in this set?
Yeah.
Yeah, so xn minus x less epsilon over 2.
Oh, okay.
Not equal to, it's strictly less. We're so good. All right, guys, let's try the other direction. The other direction is where we're gonna have to work. Proving the forward direction is sort of the heavier lift here. And in fact, before I can even prove the forward direction, I'm gonna need a little lemma. Need a little lemma here. So for the forward direction, we try to prove this now. And for this, we need what is referred to in the book as lemma 3.3. Okay, so I actually am going to prove this intermediate result first. And what this result is that a Cauchy sequence is bounded. You might remember we had a proposition a couple sections ago that said that a convergent sequence is bound, right? And we have not yet proven that Cauchy and convergent are the same thing. So I'm not allowed to just say, oh, well, this is just coming from that other result, right? So we do know that convergent sequences are bounded, but that doesn't mean that Cauchy sequences are bounded, because we have not yet proven that Cauchy sequences are convergent. In fact, that's what we're in the middle of trying to do right now. So this actually needs a proof. We actually need to prove it. It's going to look very similar to the proof we gave a couple sections ago that a convergent sequence is always bounded. So I'm going to give you guys a choice. We can either just take the lemma for free right now and see how the rest of the proof goes from there, or I can, and then come back and prove the lemma afterwards, or we can just prove the lemma right now and then do the rest of the proof. Anybody care? You want to see the lemma proof? Okay, sounds good. I don't care. I really don't. I'm wide open here. Like, I'm just want to make my customers happy.
Proof of lemma. We'll prove the lemma first. Probably makes sense to do that. Okay, so let's prove the lemma first. So let's let xn be Cauchy. If xn is Cauchy, then that means this definition is true. Meaning for every epsilon, we can find an n naught. I'm actually going to pick an epsilon now. Namely, I'm going to let epsilon equal to 1. This proof is going to look very similar to the proof that convergent sequences are bounded. It's going to go very similar to that. Okay, so there's my epsilon. So what's my definition tell me? Well, by definition, there exists an n naught in the natural numbers such that if what n comma m is greater than or equal to n naught, then the absolute value of xn minus xm is less than whatever the epsilon was, which was 1. We chose epsilon to be 1, so we would have that. So if I pin the m value to be n naught, this statement would be true for any n greater than or equal to n naught, as long as m was like pinned down at the value of n naught. So in particular, let's add that here. In particular, see, I have 2 parameters floating around here, and I just want to get rid of one of them. So in particular, if n is greater than or equal to n naught, then the absolute value of xn minus xn naught is less than 1. So I originally had both an n and an m, but I'm going to choose m to be n naught. So this inequality just gets changed to, I have both n and m are free to roam around greater than n naught, but I can pin the m value to be equal to n naught and still have a true statement for all values of n greater than or equal to n naught. So this is what we need to do here. And so thus, if n is greater than or equal to n naught, then how big can xn be? I'm trying to show that this sequence is bounded. Well, the biggest that xn could be would be maybe 1 unit larger than whatever xn naught was, because these two can't be very far apart. These two are stuck within 1 unit of each other. So this value here, at worst, it could be as big as 1 plus absolute xn naught. And that's a fixed value. That is a fixed value that we have there. Okay? So that's for all n greater than or equal to n naught. The xn terms are bounded by this much. But now let me do a final bound. I'm going to call it b. This is going to be the bound for the entire sequence. And what it is going to be, my friends, is the max. This should look some kind of familiar, guys, from a result that we did a couple weeks ago. So this is the max of absolute x1, absolute x2, ... all the way up to absolute of x n naught minus 1. So the first few terms we can't really control, but that's finitely many numbers. And then we'll control the rest of the terms by using this fixed value of 1 plus absolute x n naught. This is our b value. And so now the point is, then absolute xn is less than or equal to b for all n. X1 is less than b, x2 is less than b, x3 is less than b, right? These first finitely many are certainly less than or equal to this max that we've just taken, right? So x1, x2, x3, those are all less than or equal to b. What about after we get up to the n naught term? Well, any term xn that is greater than or equal to n naught is bounded above by this much. Okay. Notice I'm taking a max of just a finite list of numbers. It doesn't go on forever, right? This is basically n naught values. And so you can take a max of those. This max will not be plus infinity or any weird thing like that. It will actually be a fixed value. That proves this lemma. That's going to prove the lemma there. Okay. So now only have a couple minutes, but I think I can now, I think, finish the proof of this theorem 3.12. I have enough time. It's not very long, but you can see it takes a little bit of time. Is everybody with me? All right, let's now proceed. I already drew my arrow. I'll just draw it again. Yeah, I just had to do this little side lemma. Now I'm going to start over. We're going to do the forward arrow, and I'm going to assume that what am I doing? I'm assuming that xn is Cauchy. Assume xn is Cauchy. And I want to prove that it converges. So I'm going to need to figure out what it converges to help me work through the proof of this. But what I will say is that thus, by lemma 3.3, xn is bounded. Okay, so our sequence is bounded. We have a bounded sequence. Bounded sequence. We do anything with a bounded sequence? The Bolzano-Weierstrass theorem. I told you guys this is an important theorem, and it is absolutely, it's probably the most important theorem in chapter 3, right? That every bounded sequence contains a convergent subsequence. So by the BW theorem, this is a good way to kind of wrap up today, is to bring that theorem back into the limelight one more time. By the Bolzano-Weierstrass theorem, which is 3.10, there exists a convergent subsequence. Let me call it XNK. And let's just say it converges to X. All right. Well, so then what my claim is going to be, that I have 2 minutes to prove. That's all I need. It's quick. We're almost there. The claim is going to be, what are we trying to do? We're trying to prove that xn converges. We now have a candidate on the table, which is this x that the Bolzano-Weierstrass theorem just gave us. I'm going to claim that xn converges to x. This is exactly what I want to do. And I'm just going to do it from the definition of convergence. Okay, so let me set this up here because I want to get this proof looking nice. Let's prove this from the definition. Let epsilon greater than 0 be given. Now, because the sequence is Cauchy, that's our assumption, there already exists an n naught in the context of this definition, right? So, except I'm not going to call it n naught. So by definition, there exists, I'll call it L. I think this is the book decided to call it capital L. There exists an L in the natural numbers such that if n and m are greater than or equal to L, then the absolute value of xn minus xm is less than anything I want to put here. And I'm not going to leave you in suspense since I'm running out of time, but we're going to need to make it epsilon over 2. Okay. If you prefer to use N1 and N2, because I know we've been doing that a lot instead of this L, that's also fine. I'm just using the book's notation. So there exists an L because the sequence is Cauchy, there exists an L such that blah, blah, blah. Okay, beautiful. Similarly, just give me an extra second here, guys, to finish this up. There also exists an M in the natural numbers. This would be like an N2. Now, what I'm doing with this, guys, is I'm using this guy. We have a subsequence that converges to X. So for all epsilon, there exists an N2, or in this case, an M, such that if K, I'm gonna call it K rather than N here. If K is greater than or equal to M, then absolute X and K minus X is also less than whatever I want. And whatever I want here is again going to be epsilon over 2. Okay, so real quick, let's finish this up. I'm now going to let P be the max of L and M. This is really the N naught that we need to find. Okay, so sorry for the L, M, and P. If you prefer, you can use N1, N2, and N naught. It's the same thing. But what I'm going to do now is I'm going to assume that N is greater than or equal to P. And I'm then going to look at the absolute value of Xn minus X. I want that to be less than epsilon, right? Well, guys, we're going to do the same trick that we just did in the other part of the proof. We're going to add and subtract something in the middle here. I'm going to subtract XNP and then add XNP in the middle of that absolute value. Just going to add and subtract that same thing. Then I'm going to use the triangle inequality to write this as less than or equal to the absolute value of Xn minus XNP plus the absolute value of XNP minus X. And now the idea is that, well, the idea is, so look at this second term with me first, guys. XNP. P is bigger than K. Just a second. P is bigger than M. Sorry. P is bigger than M because it's the max. So P is at least as big as M, and anything that's at least as big as M when it's a subscript here gets you less than epsilon over 2. That's less than epsilon over 2, right? How about this one here? Well, as long as both of my subscripts are greater than or equal to L, that'll be less than epsilon over 2. Let's check these subscripts out. N. N is greater than or equal to P. P is greater than or equal to L. Great. So N is greater than or equal to L. N sub P is certainly greater than or equal to P. Because remember, it's a strictly increasing function. So, and P is greater than or equal to L again. So both of these subscripts, guys, are, well, they're both greater than or equal to P, which is greater than or equal to L. So this is also epsilon over 2, and we are done. And I'm so sorry, I got a little carried away today. You're getting extra 4 minutes for your tuition dollars. We look at it that way. I hope that makes sense. I'm sorry it was a little bit rushed at the end, but I can take questions on that later if anybody wants to check on it. That's our theorem. On Thursday, we'll do an example or two of that, and then we're going to move on to chapter 4. I will see you guys next time. Thanks for being here.